finding the equation of least squares line of best fit. We've been introduced to a line of best fit by eye that would let us make predictions about numerical data in a scatter plot. I'm going to introduce you to the concept of the least squares line, which your calculator will calculate for you. We'll actually go through how it's done, or at least a description of it, and why it's called a least squares line later. For now, it's important to just be able to get the equation of a line of best fit and get it onto the graphics calculator. So here I have the height in centimeters versus the weight in kilograms of 11 people. And they've said find the equation of the least squares line. You should already know how to get your data into your graphics calculator. So I've done it here. If you don't remember how, do check in with me or watch a previous video. Remember, of course, that your x, your explanatory variable, is always in L1. Your response variable is always in L2. To get the equation of the least squares line, you're actually going to do the same thing that you do to get r and r squared. That is going to be stat, move across to calc, so let's get these happening, quit out of that. Stat, calc, Linreg, so 4 is Linreg. Now, if you just move down to calculate, then you'll see that we get this display that we're quite used to. Let's see if I can get that a little bit clearer. And you'll notice that we've just focused on r and r squared up till now. But here I've got y equals ax plus b, a equals this, b equals that. Now when you look at y equals ax plus b, you should realize that that looks pretty similar to y equals mx plus b, the equation of a straight line. All that's happening is that your graphics calculator gives this as a instead of m. So a is the gradient, and b is the y-intercept, and you'd normally take it to 2 or 3 decimal places, and of course we go to calculate there. So the equation of my line, going from the graphics calculator, is y equals 0.867x minus 84.8, and it would depend how many decimal places we were asked for. So that's our gradient, that's our y-intercept. Now that is enough just to get you the equation of the line. You can also plot the line on your graphics calculator, but to do that you do need another couple of steps. We still do stat, calc, 4 is Linreg. Sorry about moving my page around everywhere here. Stat, calc, Linreg. But instead of moving straight down to calculate, we're going to come down to store. Now what this is saying is that I would like to store the equation of my line of best fit in the y equals, where the graphics calculator will know to graph it when I do my scatter plot. But to do that, we've got to say store this equation in y1. Let's hop out, because remember when we go in here, there's got y1, y2, all the rest of it, and I want it to store it in y1. So stat, calc, Linreg, come down to store, but to get y1 it's a bit tricky. So I'm just going to put that here. To get y1, you go to the button marked variables, vars. It looks like vars, I know. You go across to the y variables and select one function and one y1. And now I've got y1 in there. So variables across to y variables. One is function, one is y1. And I'm running out of space here, but that after, so you go stat, calc, linreg, and the store is y1. Now it can be a little bit different on the various types of calculators. I'm really happy to go through the different sorts. Now that I've done that, you go down to calculate. And now, if I do zoom 9, it will plot my scatter plot with my line of best fit. I have probably going to need to make sure that the x value goes at 0 and the y value goes at 0. We'll talk about getting a really good graph size showing, because you'll see that the y-intercept wasn't showing before. So when you do zoom 9, this is not the y-intercept. This is just looking at how this passes through your data alone. So as you saw when I did graph, I've gone zoom 9 now, all of this is clustered up one little side of the scatter plot. Never mind about the little window thing there, but zoom 9 will let you see where this goes through your data. So that is how to find the equation. You might be asked to either interpret the gradient and intercept or to write the equation of the line with, instead of y and x, the variables that you're using. So y was weight. Weight equals 0.867 times height, or x, minus 84.8. If we are asked to interpret the gradient, a gradient of 0.867 says that your weight increases by this much for every 1 centimetre increase in height. We know it's centimetres because it's up here. Sorry, my writing went wonky again. Weight increases by this amount for every 1 centimetre increase in height. A y-intercept of negative 84.8 implies at 0 centimetres, weight is negative 84.8 kilograms. Obviously, this is extrapolation way outside of my data. My data is all up here where x is in the 170, 180 range. Coming all the way back down to x equals 0 for the y-intercept is a really ridiculous y-intercept. A lot of the time the lines aren't that meaningful outside where the data is, and so extrapolation can get some very funny numbers. But we have at least interpreted the y-intercept.